Hey everyone, welcome to this really awesome webinar about databases. This is again going to be focused a little bit more on the game tech scenarios and game tech customers, but we've got a lot of really awesome stuff to lined up for you today. Before we go into the objectives of today's webinar, I guess we should introduce ourselves, right?
Yes.
Yeah, so hi everyone, I'm Nick Walsh and I'm a developer advocate at AWS, and what I do is I help developers everywhere leverage cloud computing.
And my name is Tabitha Graves. I'm the Community Enablement Manager at AWS Game Tech. And my role here is to listen and speak with game developers of any size about how they can use AWS resources for current and future game development.
Wonderful. So Tabitha and I are teaming up today to deliver this content for you. And before we get into any of the specifics, I figure we could cover a little bit about what folks could expect in today's webinar. Does that sound good?
Yeah, no, that sounds awesome.
Yeah, so again, we're assuming in this webinar that folks may have never used a database before and may not know anything about how to leverage them or decide between the ones to use. So, starting from the 10,000 feet, we're going to talk a little bit about databases broadly. And then over the course of today's webinar, we'll narrow in on the different scenarios where each of the different types of databases is going to be the best tool for that given job.
Yeah, there are a lot of options out there, and we want to make sure that as we are talking today about not just specific AWS services, but different use cases for how you can use databases in your game development.
Exactly. So even if you're not sure about the exact syntax of the databases, you're going to be, the code you're going to be writing. We hope that you'll leave today's webinar with some solid examples of what databases will be best suited for specific scenarios that you probably face as a game developer.
Awesome. So without further ado, let's get started. All right. So starting at the beginning, let's look at what is a database. So a database is basically an electronic system for storing, managing, and retrieving data. A very basic version of this is going to be a flat file database, which is basically just lines of text separated by delimiters. But it's something very simple, and in a single non-connected single-player game, you can see this with save game data. The major differences in databases are structure and modeling. So the more complex the structure in the model, the more features and capabilities that you would have in your database, like you see below in the bullet points.
Yeah, no, when it comes to optimizing storage and retrieval, we see in the most basic example of trying to electronically store data, a flat file may be performant, right? In a single player game where you have very specific and known access patterns for reading and writing, that may be all that you need, right? You don't want to bloat your system with more than you necessarily may need. Yeah. But as we can see that in the advent of performance-oriented games that need to work with low latency across maybe multiple different clients that are reading and writing at one time, we see that there are a lot of other constraints that start to come into play. And so that, like Tabitha mentioned, there are lots of different database technologies, both springing up from the different forms of modeling data, but also from the different performance constraints that we find. And you'll see that in the different database types that we'll go into in just a little bit, all again, while still trying to maintain concepts that are fundamental to data, right? Like security, durability, the ability to scale out reads and writes for data. These are all fundamental to accessing, storing, and maintaining data. So next, let's talk a little bit about how game developers broadly can benefit from databases. Obviously, it's important to be able to access your data quickly, securely, and make sure that it's durable. But what we've found is that as the game industry has progressed, games have increasingly become fragmented in where their data may live, but also where it needs to be synchronized. In worlds where games are increasingly online with more and more players, being able to have a database or a data management system that can do things like syncing data reads and writes from the client to the server to backups and multiple systems that may exist in some sort of mature pipeline are ultimately necessary. And so while there are ways to implement sort of simple and rudimentary processes without a database, they really become sort of critical at a certain point when you're scaling this out and trying to keep all of these data stakeholders sort of in line.
So a lot of game developers will ask, what is the major difference between what game developers do now versus taking their databases and hosting it in the cloud? So currently, a lot of game development studios will actually host their databases are on premises. So a lot of the overhead, a lot of the network resources, the database management, all of that is onto the game developers and the people who are managing that.
Yeah, this is introducing a concept that we like to call at AWS called managed services. Mm-hmm. We talk a lot about this thing called undifferentiated heavy lifting, which is a which is a concept that, in short, boils down to if it doesn't provide you benefit to your application or to your end user, customer, or in this case, player, you don't really want to spend your time or money doing it. And so it's much more efficient for some of these game studios to use managed services where AWS, on behalf of the customer, manages things like security, the infrastructure and the power around that, security of data centers, so that developers can focus instead on writing application code for their games, websites, and supporting applications.
And ultimately, you also optimize your ability to improve upon these player experiences. So you eliminate certain resource constraints that might hinder the actual player journey.
Yeah, with resources being able to be provisioned at a moment's notice or even in a completely automated fashion, you can guarantee that the system you introduce today will have automated mechanisms for scaling up as you increase traffic, but also will have ways that you can fine-tune it as your workflows or workloads may change over time as your game evolves.
Yeah, and this is very relevant to any game studio. So from indies to large studios, these resources are built to scale with your game that you're developing.
All right, so let's talk a little bit about how I decide which databases, right? Because there's going to be a lot of them. And I know we'll get into the details around exactly how to perform that mental math. But broadly, how do we think about choosing a database?
So there's a lot of questions surrounding that. So a popular question is going to be, if I'm already currently using a database on premises, like PostgreSQL or MongoDB, how exactly would I go to migrating into something like the cloud?
Exactly. That introduces a concept that we refer to as lift and shift, essentially taking a workload or in this case, a database, and essentially imitating the software deployment that you have on premises, but in the cloud, and reaping the benefits of managed services and the resiliency and on-demand aspects of cloud. There are lots of other instances where a developer that may be listening may have never used a database before, and they may actually have to be thinking about for the first time either how to model or remodel their data, or from existing data that they already have that's modeled in some way, shape, or form, which database will be ideal for being able to productionalize that data. So there's a lot of concepts from data modeling to access patterns to just developer familiarity or what infrastructure you're already bringing to the table. These are all going to sort of bubble up into the decision-making process for which database will be best for you.
Yeah, exactly. And a lot of the use cases that we will talk about today, hopefully you'll get a sense of, what applies to your type of game development that you're doing currently, and you'd be able to apply it appropriately. So we are actually going to be discussing 6 different AWS services today. And they're all very different from each other, not just from the use cases, but exactly from the structures and the different models or the way that they are modeled.
Yeah, I'm not going to dive too deep into any of them right here, but broadly, again, keep in mind, we want to use the right tool for the right job.
And I really like what you said earlier about optimizing. It's not about which database is right for you. It's about the different workloads and how you want to utilize the database and then optimizing the capabilities.
Yeah, and oftentimes, this people make the joke that life imitates art. It's a lot of these databases actually have come in the progression of history as a result of there being suboptimal sort of scenarios and cases with some of the original databases. So these tools have spawned from the need for them to exist. These all didn't sort of just pop up as different opinionated takes of all trying to solve the same problem. These have evolved specifically to tackle certain problems, and I think that'll be really clear when people can see the use cases that they cover.
Great. Well, let's look at the first one. So first, we're going to look at relational databases. So relational databases are based on the relational model of data, meaning everything is stored as a collection of tables called relations. So inside these tables, the relationships of data are stored in predefined row and column structure, which actually allows for more performant reads. An example of a relational database engine would be something like SQL, PostgreSQL, Oracle, and a very special one, Amazon Aurora.
Yeah, Amazon Aurora, we love to say that it is the relational database built for the cloud, because when we think about managed services and the ability to scale up and out where applicable, Aurora is really where we see this come into its own, with the ability to separately scale out reads and writes so that you're ultimately, at the end of the day, only paying for the value that you're receiving, rather than just trying to pay for arbitrary server units that have fixed sort of increments of compute, storage, and memory. we find that even for a given data model, like in this example, relational tabular data, that can fit into what can be best described as sort of like a spreadsheet, where every sort of column is a feature, and then every row is a different item. What we find is that even for one given set of data, by having to perform reads or writes separately, or multiple customers having reads and write patterns that are fundamentally different, necessitate different optimal scale-up procedures. And so Amazon Aurora finally enables this by having separate data storage and compute layers for resolving these queries. Aurora fits into Amazon RDS, Relational Database Services, which is our broader relational database offering that enables powering from many different types of database engines. You mentioned a lot of them before: MySQL, Postgres, Oracle, and so on.
So if there is a developer who currently uses Postgres on premises, how exactly does that look if they are looking to move, to the cloud or to Amazon Aurora?
Yeah, so we have two sort of parts to this migration, I guess. First is actually getting your data from the on-premises database into Amazon Aurora. Now, the easiest way to do that, I would say, is outside of trying to manually try to do that, which is not easy. Use something like Amazon DMS, Database Migration Service. I believe that's the right acronym. But essentially, that's actually a software tool that enables you to plug in proverbially to your existing database, plug into Aurora as the destination with a table that you may have spun up already, or a database instance that you've spun up. And it will actually facilitate that transfer of data. Now, you've now lifted and shifted essentially your data from the on-prem database to the cloud database in Aurora. But now you're probably wondering, well, how does my code have to change? My code was used to querying my on-prem Postgres instance or Postgres database. And this is where the Postgres compatible aspect comes in. So the idea here is, because the developer-facing engine or interface for Aurora will still be Postgres, you can still bring those same bindings that you used in the same application code that worked with accessing the on-prem version to the cloud here to access Aurora Postgres.
Aurora acts the same and has the same basic structure as like Postgres or MySQL, but it can be faster.
Yeah, so that's a really good point. So sometimes when we say things like compatible, what that means is that it's not simply a hosted version on the cloud of that identical Postgres engine, for example, right? What we can actually do here at AWS through these hosted and managed services is offer a developer interface for these reads, writes, and basic CRUD operations, any operations you'd want to perform in your traditional Postgres applications, but we can use that as a front to a different engine that we've optimized, knowing the hardware and infrastructure that we are going to run those databases on. And so this is really where it all comes together when we say it's the relational database built for the cloud. There are a lot of constraints that may not exist in a data center that we run and operate and manage versus just running open source software anywhere. So we kind of try and take the best of both worlds approach, where we can continue the same sort of developer experience and bindings that developers know and love about tools like Postgres, but optimize the infrastructure under the hood to work really, really well on our infrastructure.
Great. So how do we apply this to game development examples? So a major one, as you can see, a lot of data, so player data, game data. But also it makes sense to have something like player and game data to be structured in this way to be highly performant. So another example would be, if you are designing a capability or a feature in your game to keep track of matchmaking rating or MMR, in the table, a key could be your player username, and then the other values could be rank, matches played, matches won, lost. You can add this capability using that.
Yeah, I think more than anything, what defines the best use case for the relational databases like Aurora are going to be instances where you have either you have fairly consistent shape, is what we would call it, for your different items. To describe where relational databases are not great or are good, or to almost start diving into where they're not great. Broadly, in the same way that we fit into this relational data model, every single column needs to have a value. And where this starts to become inefficient is when you have a database table, imagine a spreadsheet, where you're trying to store many different types of items, where you may be talking about player data, where you have a bunch of stats for your players, for example, but you're also storing values for items in that same database. So items may not have health or mana, for example, like a player may have. And now ultimately you still need to have values in a relational model for those given features or columns. This is where it starts to become inefficient, where you have a bunch of essentially dummy variables that don't provide value. So you may want to then distribute those, you have multiple different tables to make that efficient. If you know your data, if you can understand and thoughtfully craft a bunch of columns to make it efficient, or you have a bunch of items that you know for a fact will all have a very consistent type of shape to them, then it becomes very performant to use the relational database. But we know that's not always the case, right? Sometimes you don't know how your data will change over time, and sometimes when you're just starting off, it may be more performant to just throw all your data in there, but we'll start to see later on how there are a lot of scenarios where that doesn't become the best. But again, things like high scores, item shops, inventory, game and player data, typically these are not going to change drastically over time. And for every entity like a player in your game, they're probably going to have the same core fundamental health, resources, or statistics. And so relational fits really well into that.
And that was a good point that you brought up, which actually lets us transition to the next database.
Yeah, so next up is non-relational. This is sometimes a bit of a misnomer. People have a lot of opinions on this because I would argue that all data is relational and that they're related in some way, shape, or form. But this is the standard nomenclature. But I think the more common and apt way is defining NoSQL, right, for this database sort of offering. Yeah, so for NoSQL, essentially, if you think about relational data being sort of locked into columns in a spreadsheet type of format, non-relational is essentially anything that would not be relational by nature. And so this starts to introduce the idea of having variable item shapes, items being entries, or imagine them rows in a table, but now items can be, in some sort of object notation like JSON. They can vary in the keys and values that each of them store. Ultimately, they start to bring in flexibility. And your queries are typically querying specific keys on those values or values on those objects, or keys and values on those objects, essentially. But with all of this flexibility comes some sort of trade-offs. So ideas like eventual consistency rather than ACID compliance in relational databases starts to come into play.
So a non-relational database, I think this is the first of the non-relational databases that we will be discussing today, is DynamoDB.
Yeah, DynamoDB is really the quintessential NoSQL database for so long as all of your data sort of fits under the given properties for it. Broadly, instead of doing queries on values across an entire table, what you're doing here is you're essentially iterating across the keys and values for the different items. Keys and values, again, you're defining some very specific terms, hashes oftentimes, and those will resolve to certain values. And you're typically trying to find those values for a given set of keys or key. Broadly, DynamoDB, extremely performant, extremely low latency for some of the most common CRUD operations. And when it comes to managed services, I think Dynamo is really one of the most standout ones because you don't have to manage any of the underlying instances, servers, or anything. You basically, in the GUI and in the AWS console, can create a database. Collection is what it's called, or a table, and you can instantly start inputting or inserting items into it, performing reads on it. And as you're trying to build applications to scale out on this, you have these arbitrary components called read units and write units. So no longer do you have to sort of think, how many read units fit into a server and when should I scale up and when should I scale down? That's all automated and handled behind the scenes for you. So as long as you can see the access patterns and take a look at those, you don't have to worry about waiting in a scenario where your reads or writes sort of spike at one point in time. They'll automatically scale out for you. And there's lots of intelligent ways of pre-provisioning read and write capacity to save even more money, and so on and so forth. But essentially fully managed, full flexibility of the sort of the key value NoSQL interface. And the first place I'd point anyone who doesn't want to look at a relational database.
So you mentioned fully managed, and I know this is something we also covered a little bit earlier in the presentation, but I think it's a pretty important point to reiterate on. What does fully managed mean as in terms of a AWS service?
Yeah, so fully managed essentially means that any of the keeping the lights on components of running an application are handled on behalf. AWS handles them on behalf of the customer, and that's built into the pricing. So components to this go all the way down to the physical land that a server or an instance runs on, then the security for that data center, the power that goes into it, oftentimes redundancy from a infrastructure perspective across multiple availability zones, all priced into that. So essentially, it all boils up to this concept that the developer doesn't need to worry about anything below that on the stack. And in DynamoDB's example, in DynamoDB's case rather, this means that developers don't have to worry about anything beyond the developer experience of querying and creating tables. They don't even have to worry about provisioning infrastructure or servers because that is completely abstracted away from them. Another thing that's really nice to call out here is security. So oftentimes when folks are running some sort of engine for any application, but databases in particular, when a new version comes out or there's a security flaw that's implemented or discovered, it is up to the company that manages that software or the database admin commonly at game studios to patch that version of the engine that they're running. Otherwise, they're standing at the risk of being able to have their data be exploited in one way, shape, or form. Using AWS services, those are managed and maintained on the customer's behalf so that they can have the peace of mind that, as long as they're following the best practices and everything that we recommend to them, that they're running state-of-the-art security essentially on their instances, clusters, or in DynamoDB's case, services. And before we go into the use cases that Dynamo really shines in, the other databases we're going to get into, a lot of them actually start to break out of the data modeling question and start to break into the optimization around queries or the types of data you may be storing. So relational versus non-relational is a very big jump, but we'll start to see that even in non-relational world or in NoSQL world, the differences are not as clear all of the time as to which will be best, but they optimize for different things.
So game development examples for either DynamoDB or a non-relational database. So a good one, enchantments and upgrades. As Nick was mentioning before with the different collections or the tables, the way that that's structured with non-relational databases, you can actually join two different tables together. So if you have, for enchantments and upgrades, if you have one table has your basic player stats, then you have another table that has player stats but with an enchantment. You can then, run a query to see the OP results that would give you your player in the game.
Yeah, ultimately, when you have this sort of key value structure, these joins become easier because you're just appending items into an existing database or appending keys into existing items, essentially, instead of having to, imagine in relational world, you have this big table you need to combine two, or you have multiple tables, you need to combine them. You need to sort of see what the common columns are between the two and try not to overwrite or resolve those conflicts on a merge, and ultimately sort of deconstruct those tables and merge them together. Joins in relational database world are their own sort of entity entirely that people are very passionate about and are not often very simple. So key value databases make that significantly easier.
So here's a question, and I know, in our other previous slide, we were talking about game development examples, game data for relational databases was also there. What would the difference be for, storing your game data in this case?
Yeah, so I think that in this case for Dynamo, this becomes really valuable when you may have a lot of entities that you need to query, and it makes sense for them to all be in one sort of database collection, even if they have variable object and key sizes. Additionally, you may have insight into parts of your data for, parts of the world. Here's one example, right? If there's one part of the world where a player is in, and then you have to design a game client that is going to efficiently be able to query maybe the NPCs, enemies, items in that area, you can have this key that you've crafted based on location or use that as a sort key. And in non-relational DynamoDB world, that makes that query far more performant. Whereas in a relational database scenario, typically you'd have to perform something like a scan, or you could understand that there's a certain block in your a block in your table where you've begun items or entities that exist in a certain world. But think in relational database world, you're much more scanning and then trying to find a sort of a block of items that may fit your resolution before coming up with your exact items or your data that you need. Whereas in DynamoDB world, you can essentially craft your keys in such a way where you're going to traverse sort of the entirety of your collection in a much more performant fashion. So, like you have a world, you have subregions, you have even smaller regions within that, and you can perform all of these. You can have these secondary indexes. You can have these sort keys that enable that traversal much quicker with a smaller number of hops. Which again, at the end of the day, just comes down to how well do you know your data. And there are scenarios in DynamoDB where even though it's non-relational or NoSQL, your data very much has relationships within it, which is why I mentioned when I started that there is some relationality to the data, and understanding that can make that super performant. Now, disk space and HDD space is significantly cheaper than in-memory space or RAM. Now, this also has the trade-off of the time it takes to read and perform these operations. So separate from processor speed, it simply takes significantly longer to read from disk than it does to read from memory, probably in the order of like 10x in certain scenarios. And so the industry has faced scenarios where they need to be able to perform these operations really, really, really quickly. There are lots of other scenarios in this broader sort of field called caching, where you want to be able to have your data available. And by understanding sort of how your data is used, like if I access it, will I access it again an hour from now, therefore keep it hot in my cache? This same technology applies to databases, not just like local content from your browser, where it makes the page load faster, right? So we have in-memory databases. They're extremely fast and performant because they're reading from memory. Typically, these are key and value. So when a key has been searched and the value has been returned to the user, we'll also store that in the in-memory database or in the cache, so that if that same key gets looked up either by the same one client or a different one, instead of having to hit the database again for a slow, costly read or write, or typically a read, the in-memory database can simply read that same key directly from disk because it has it there in the cache, and return that value in a very, very timely fashion. There's lots of intelligence or tricks that in-memory databases can do around searches and sorts, as long as that data is in the cache. And so this is typically put in between sort of your database, that is your golden source of truth, and the client, so that again it takes requests away from the database. Continuing the trend of fully managed services here, again, it's a fully managed caching layer that is, offers a lot of the common engines for that and interfaces. So Redis and Memcached are currently supported as engines for Elasticache. And again, in the same way that it's compatible with them, you can just bring your existing code that works with maybe your own self-hosted version of Redis or your self-hosted version of Memcached that runs on-prem or in a co-location center. If you have a cache that you wanted to be closer to your players, you can sort of lift and shift that workload and put that caching layer in front of any sort of database. And so obviously Elasticache is very performant and it's scalable. But this is where I would love to talk about how even for a given project, one database may not be all that you need. So I've alluded to Elasticache working in tandem with other databases. But essentially, this is actually like the most common case, I'd say, for Elasticache, where you have a client that performs those operations for reads, writes, updates, and deletes. You have a server that exists somewhere, in the cloud, or you may have multiple tables, what have you. But ultimately, you may have reasons to believe, or you have trends in your data where players may query one item or one player's information, and then multiple other players are going to query that. So there are patterns for, well, if I can have that data in memory and keep that data that's hot more available to my players, I can reduce the costly reads to my database, return the data faster, and ultimately reduce the amount of scale out that I need on my database layer. Because even though every one of those requests to your database will resolve to the same value in the example of a read, like, hey, what is that item that player has, right? Maybe someone just got really awesome loot. They ran into town. Now everyone wants to know what that gear is. Instead of having every single one of those players have to perform the same read, perform the computation to query that item and get that result, once that first player has done that, you can throw that in a cache. And then every single player's request that hits the cache will just really quickly return the results that have already been sort of like kept on ice there. That's actually a bad analogy because it's hot data, not cold data. But you get what I'm saying. Like it becomes available for the player quicker, and you can essentially reduce the size of your database cluster as a result.
Let's look at some game examples. So with game development, you were even saying before, as far as looking at utilizing Elasticache in front of another database to boost the performance. My favorite example would be something like a leaderboard. I know putting Elasticache in front of, Dynamodb, Elasticache would handle the key values of like a player ID, the rank, and then Dynamodb can store the supporting leaderboard data. So add embellishment if needed alongside the actual player rankings.
Yeah, this is when it comes to caching, like all of these types of data are valuable here. The thing I just want to really double down on is really understanding the access patterns for your data. Mm-hmm. So one of the most complicated parts of optimizing a cache is defining what's called an eviction policy. I won't go too deep into it, but basically your cache is going to be very small compared to the overall size of your database, again, because RAM is more expensive than hard disk space. Otherwise, we just run all of our databases in memory and this problem would go away. And so as a result, you need to figure out, well, my cache is filled with data. When do I remove an item and add a new item into the cache? And a lot of that comes down to, in this case, in gaming, player behavior. So for example, it doesn't make sense to keep data in a cache if a player is expected to have if they've just signed out and are likely not to need any queries related to their data in particular, right? So that could be a condition where we evict them from the cache, right? So if they're online or not, that could be the most basic implementation of a cache where, maybe 10% of your players on at one time, and you can simply just throw all of your player data for a player who has signed on and has not signed off yet into the cache. This becomes more complicated over time, obviously, when you have other sort of things like maybe you're trying to query historical data and multiple different players can all query that. Maybe you have local caches that are specific to those time zones in that region where player traffic may spike. There's lots of different ways you can sort of make the cookie crumble. But really understanding the access patterns is key to making an effective and a cost-effective cache.
So moving on to the next database, you're actually going to notice that with document databases, a lot of the values here are very similar to another database that we previously discussed.
The idea here with documents in comparison to items and objects is that objects while they may have variability in structure, the idea is that the level of nesting should hopefully be somewhat similar. So you may have a bunch of keys and values, but the embeddedness and the levels of depth within them should hopefully be somewhat consistent. Otherwise, that may not be necessarily performant. Additionally, in a key and value, what we're thinking of here is small items. So this doesn't necessarily mean that there aren't a lot of items in the database, and it doesn't mean that there may not be a lot of keys and a lot of keys. But in particular, we're thinking about text and strings, and so by understanding and implementing a constraint at the database engine layer, that again helps it be more performant. Now, when we think that not all data sort of fits into that constraint, right? So when we have very many layers of nesting in our data, when we may have very large items or values. So for example, if you're making a game where there's a certain audio file that may play or trigger for that given object, you may want to embed that directly into the item or object itself. And so we like to call these documents. A document is an entity or what would be an item in Dynamo that could represent any sort of shape, could represent any level of depth that includes depth and number of keys and values and the variety within them or between them, but also for these values. So a value in Dynamodb can only be 400 kilobytes, whereas in DocumentDB that can be, which we'll get into in just a second, but in document databases generally can be much larger. So flexibility not just in size and shape, but also in the actual content of those given entries. And so from a database engine perspective, there's a lot of additional overhead, or rather the data just has to be handled in a very different way when you're changing these underlying assumptions. But I think the big thing for people to think about is just additional flexibility, even on top of the NoSQL sort of paradigm.
So good transition. Let's now talk about Amazon DocumentDB.
Yeah, I jumped the gun on it a little bit.
No, it's okay.
But DocumentDB is our AWS managed offering for a document database. So again, all the benefits of fully managed. And one of the most common ways developers are probably going to interface with this is through MongoDB. MongoDB, again, a very popular open source database offering that developers are running either on premises for their existing data needs, or maybe you're using another cloud provider or using that in the cloud somewhere. And so again, with MongoDB compatibility, that enables you to both perform an easier sort of migration for your database from your source to Amazon Document DB, but also that you have compatible bindings between them. So all of your standard CRUD operations, it's not exactly one-to-one, but we're catching up every single day to ensure that sort of closeness and compatibility.
So talking about game development examples, would you mind telling us for game dev tools?
Yeah, for game dev tools, I think that one of the biggest things here is again going to be like flexibility, that you can have they're referred to as collections in Document DB, but this collection of all of these objects that may exist, that you can guarantee that you don't have to manage multiple different connections to different databases or different data sources. A really good example here for like on-demand assets that's listed on the slide is that you may have an entity that appears in your world. And in another database like Dynamodb, where you have to have a small value, let's say this it's a creature in your world, for example, and has an associated sound that it makes, right? In Dynamodb, you may need to have a pointer to maybe Amazon S3 or another location that sound lives in, which you then have to use to go and query and fetch that sound, right? It adds a bit more complication to it. By using Document DB, you have that flexibility of actually putting all of those different assets for a given object, like that creature, maybe its texture, the sound that it makes, all in one object. So your game engine can just query that object and have essentially all of the different aspects and values from pictures, sounds, but also numerical data, strings, its name, and stats and all of that, all in one place. So a lot of flexibility, both for the developer to write the code, but also for other folks that need to access that information. For other projects in the organization that may not just be the single project or functionality you're trying to implement at one time.
Great. So now we're actually going to talk about a big trend and a super cool use case in games, ledger databases. So blockchain.
Blockchain, yeah, blockchain. Exciting word.
So blockchain is NoSQL as well. So it also provides an immutable, transparent, and cryptographically verifiable transaction log owned by a central authority. And I had to really practice saying that.
Yeah, it's a mouthful to describe ledger databases and their core functionality. I think they always become a bit more digestible when we finally get to the the use case scenario, because the use cases are often tangible, and when we describe the value proposition of them, much like blockchain sort of broadly, it becomes hard to see sometimes exactly how they can provide value.
Yeah, this sounds very intimidating. So we're gonna move on to what the AWS service for that is, and that's going to be the Amazon Quantum Ledger Database.
Yeah, so a lot of folks are really interested in blockchain broadly, and that sort of spurred us to think, right? Like, what are the key components and value propositions of blockchains that people are really excited about with respect to offering a developer tool? And so what we see there is the ability to have verifiable and auditable transaction logs that are essentially immutable, and they're owned by and those are the most important things. One of the components of blockchain that differs from ledger databases is that blockchains are essentially owned by no central authority. The protocols that define them are essentially ownerless. The blockchain verifies itself. And what we found is that developers often are the trusted central authority as opposed to the protocol being the trusted central authority. And what we've done is we developed a ledger database, QLDB in this example, that enables you to have those key value propositions of an auditable, immutable log, where the company that still builds the game is the trusted authority. And by being able to make that assumption that the game company for the game that you're playing is trusted, that is inherently very valuable. Because if you don't trust the game developer from the game that you're playing, you have some other larger issues at play. But this makes these transactions that traditionally on blockchain could be really long and energy inefficient. It makes them much more efficient because you have other ways to sort of resolve those transactions within QLDB. That's a bit of how ledger database would differ from blockchain. But really, what this is going to manifest itself in for game developers is that when your players want to be able to see changes tracked over time for an item or parts of your world, for example, where you can't go back and edit previous versions of the data, that's really where a quantum or a ledger database will come into play. It is essentially a system of record that players can all trust in, that previous versions of the chain or the ledger have not been modified.
I think that's a really important point, especially as we're diving into the game development examples. You bring up, security and trust. A lot of the use cases that we see go back to the transaction history and being able to just have more visibility into that information, to have that better player experience for, to prevent a lot of fraud in the cases of like rare items in specific games. And a good thing would be, the auction house. So in the case of an item, being able to see all the previous owners or where exactly that item came from is really important.
Yeah, I think there are a lot of really exciting experimental features that developers are looking to use or looking to implement that I think QLDB becomes really cool for. One that comes to mind for me is like, imagine in-game you have these really long-standing communities or ecosystems where you may have either property, you may have property include either like real estate or a vehicle or some complex machine or maybe like a pet, for example, where the history of that sort of item may not manifest itself in like externally facing characteristics, right? So for example, let's say a pet, it's important that you make the pet happy. It's important that you feed it, that you exercise it, and all of these things. And the reputation of the previous owners may be a testament to that. And so something like a ledger database can actually store all of that. And the game developer may not choose to surface some of these underlying values, like how fit the pet is, but the reputation of these owners is immutable in a ledger database. And so by being able to view maybe like the pedigree or the history of the owners and stuff, knowing that it can't be changed, that sort of changes the way some of these games can implement long-standing items, right? Like it's generated once and not every one of the items is the same. And by how that, the ownership has changed hands or how actions have been taken to it, the game developer can choose to surface certain parameters and hide others. And this is where like community-driven games start to become really interesting, right? And games that the given servers or ecosystems evolve over time. So lots of really exciting futuristic level stuff with QLDB. But I'm more excited to see when developers are like putting it out into the wild, because I have so many ideas, but I'm excited to see what they're doing with it.
So graph databases, to me, this is another exciting, especially talking about, in-game economy. This is another exciting use case for games right now. So graph databases actually look at the relationships between data. So those relationships can be visualized in the form of the database, making it extremely useful, especially when you are planning different things in the game development cycle.
Graph databases are the epitome of sort of like data that is interrelated. So document databases, if there's one thing you want to take away from them, it's not just the storage of interrelated data, but it's the ability to query interrelated data in a way that you can retain your sanity. And when we talk about the ways people can do that with our offering, I think that'll become a little bit more clear.
And our offering is Amazon Neptune.
Yeah, Amazon Neptune, again, managed service, I think every single one of these, right?
We've been talking about that a lot.
Yeah, and again, regardless of what your data looks like and regardless of what your access patterns or your syntax du jour or your database engine are, these properties that fully managed services help with are, again, undifferentiated heavy lifting. These are things that you are not getting unique value out of, and so by using fully managed, you can spend your time writing, again, applications, games, things that delight your customers and players. So fully managed graph database offering, and so what this entails is both the storage layer, obviously, for storing that data in a performant fashion, but also for being able to query that data. So there are a few ways that we can do that with Neptune. We can use either like Apache Tinkerpop Gremlin, Sparkle. These are interfaces and syntaxes at the CLI and SDK level that enable you to start with, let's say, for example, the root of the graph, and then with sort of dot notation as you can filter down or filter up, depending on how you want to think about it, the relationships that will result in a solution set. So, for example, if I have a graph database of all my players in a given ecosystem, and I'm trying to track down how the flow of items is going from people that have completed a raid, for example, a graph database would a really great way of doing this, because I can start at the root. I can sort of select all users that have received this item from a drop, and then try and return the solution set of like the guilds or home bases of all the players that have either bought or received items from those players, right? This is another way you can compare that solution set to players that have ended up with that item that didn't do it on a trade, and so you can try and detect if someone like duplicated or created an item out of thin air. Lots of really easy queries in Neptune that are really powerful and otherwise be just very, very difficult.
And I'm excited to talk about the game development examples on this one, because there's just a lot of really neat, especially for visually seeing the impact of your game development and in that player experience. It's really cool. So, I mentioned earlier for modeling game economy. So if you're entering like a new item, and you talked a little bit about this, or as far as like players or in raids, entering new information, you can see the different areas that it might improve, break, or how those relationships are actually formed. But one of the really cool use cases are for looking at player game progression. So if you have, like an open world or like an MMO or something, and you have different quest lines, and if you are introducing a new quest, you can actually see, if the player has objectives to go from in a certain zone, like quest 1 to quest 2 to quest 3. By introducing quest 3, if maybe sometimes it might make the player repeat different objectives, you want to make sure that by introducing the quest 3, it actually progresses the player through that zone. And it's just a really neat way of being able to like visually see the impact of that.
Yeah, so separate from Neptune, but playing very nicely with it are a large number of ways of being able to visualize your data, much like you mentioned. A lot of the other databases in both SQL and NoSQL, the SDK and those respective query languages are where you're going to live and spend most of your time. But Neptune is really, really fun because, and graph databases generally, because these entities and relationships, I like to think about them in my head as sort of like nodes and edges, circles and lines that connect all of these entities together and relationships together in your database. And so there are a large number of open source graph data visualization tools that can work with the RDF, the open standard for sort of graph data storage that Neptune works off of, to be able to visualize this and mess around and actually perform filters and perform these queries. And again, graph is inherently sort of this visual representation of these relationships. And I think it's, even if you're not sure exactly what your explanation or your exploration is going to be with your data, if it's highly interrelated and you're trying to perform this exploration, essentially, Neptune and those open source graphical interfaces that can work directly in the browser that plug into Neptune are a great way to start.
You could also see the hierarchy of data that you're entering, which is really important as we're talking about the different like visualizations, with the different quest, example that I brought up earlier. You can see the hierarchy of the different quests that you have like actually in that zone. So I know that was a lot to unpack. We just covered 6 different services, all very different structures, different ways that they're modeled. But I think it's really important to remember that AWS has a database for every use case. And, whether it's mobile, console, PC, all the different genres of games, there's always creative ways of making the database work for your development use case and ultimately improve the player experience.
Yeah, at the end of the day, games are becoming increasingly interconnected, increasingly online, and increasingly global. And so by being able to leverage the core benefits of managed services through AWS, regardless of what genre your game operates in, there are a lot of really, really valuable benefits to be had. But I think at the end of the day, they often boil down to some of the things that are most important to game companies, which are developer time, that you want to spend time writing your application code, not wrangling with a patch for a security update, but also in cost, right? We have these certain workloads. We may want to store our data and access it, and maybe nothing much fancier than that. We want to do that in as stress-free, but also as cheap of a way as possible while maintaining the quality that we want. So hopefully you got a glimpse of what each of those could look like depending on what your game or your workload may be. All right, so for a quick demo, I wanted to give everyone a sneak peek of what it really means to start using these databases on AWS. And I'm going to be really nailing down exactly how easy it is to get started without having to provision or manage really your own infrastructure, as that's one of the biggest pain points for folks that are using their own and managing their own on-premises databases. So here we're in home base. This is going to be the AWS Management Console. And through this search bar, we can search for any of our AWS services. So first, we're going to look for RDS, Amazon Relational Database Service. We're going to go show how easily someone can get started with something like Amazon Aurora for relational database workloads. So this is our dashboard. We can see a lot of different functionality here. We're going to go right over to databases. I have one that's already provisioned over here, but we're going to walk through creating our own. So we can click the Create Database button, and we have two options. We have the standard Create, and we also have Easy Create. If you're a little bit of a pro, you can use standard Create. That enables you a little bit more flexibility and nuance in the control. But Easy Create is, as it describes itself, as easy, and we'll actually use a lot of the best practices for those settings. We can always go back and change some of them down the line. So for configuration, I mentioned before that Aurora is just one of the very many engines that we offer through Amazon RDS, Relational Database Service. So we can click on that, but just to show you exactly how this will change, if we change each of the database engines, it will fundamentally change some of the underlying infrastructure because each engine will operate and scale slightly differently under the hood. So we're going to stick back with Amazon Aurora. As for the addition, we can actually select between MySQL or Postgres. Again, this will change sort of how the data, your interface, because your code has to directly interface with the database itself, and you'll be either writing MySQL queries or Postgres queries. But there are also performance changes between the two. Depending on your use case, you may want to decide between one or the other. Now here, we're going with MySQL, and we have different database instance sizes. So these are going to be recommended based on a dev test versus production scenario, where we may want to test our queries on a small subset of our database on dev test, and then have production on a stronger server. We see dev test being 1/10 of the cost. Or we can go into a Aurora serverless scenario, which introduces a lot of other benefits. But it's a little bit deeper than what I wanted to get into in our webinar today. As we go down, we need to give some of the basics like a identifier or a name for our database cluster. Again, a database cluster rather than a single instance, because as this may scale up or down, we will have a persistent database ID here, but the number of instances that need to actually power this under the hood may be abstracted away from us or be auto-scaling without us necessarily needing to instantiate that manually. Next, we have the master username, which we would have by default, it's admin, but let's make this more secure admin. And we'll want to auto-generate a password or provide our own if we so desire. I'm going to go with auto-generation. That way, it's something I haven't used before. And down here, we can actually take a look at all of the settings that we for when defining as a part of Easy Create. So everything from the VPC, we have a default one here, encryption enabled by default. Some of these are editable after the database is created, some are not. So you may want to keep that in mind when creating your database. But in short, if you want to just get started with MySQL on the cloud, paying per hour with managed services, you can just click create. Oh, this has too long. Secure _ admin. There we go. And so this is going to be creating our database. So we can see that right here. Our database is provisioning. The one I have started up before shows that it's available, and this one is now creating, and this will be ready in just a few moments. While this is creating, I'm going to really quickly jump over and show you Dynamo. I think that's probably the most different in relation to RDS. And so we can do that by going back here to the Management Console, going over to Dynamodb. And again, this is our dashboard home base here in Dynamo. You can see what I mentioned before around read capacity and write capacity, because in DynamoDB, it's completely serverless. You don't think about any of the underlying servers that are powering the database engine. You simply have these read and write capacity units that are dependent on the traffic that you may have. And AWS and the Dynamo engine will actually figure out how to allocate your reads and writes on underlying infrastructure completely without you having to understand that or know that. So I have a few tables here already. They have different read capacity and write capacity associated with each of them. But let's make our own really, really quickly. So we only need a few values here. So table name, this will be AWS Webinar Dynamo. We can have a partition key. So I mentioned before, a large part of the optimizations and battle with getting the most out of Dynamo is going to be understanding your access patterns and oftentimes generating keys to be able to reduce the number of jumps and skips throughout your database key value searches. So a really common one here would be ID. If we're just starting out, this could be something that's very straightforward. We could also have something like number if there's actual value in the number that we want to be able to partition by. Think about things like amount in a bank account or in a player inventory or something. We can add additional sort keys here as well, but let's avoid that for now. And with simply selecting use the default settings, we can actually very quickly create our own Dynamodb table. Again, because there's no actual server and that needs to be spun up or managed under the hood. As soon as this table is done being created, it's ready to go. You can start inserting items. You see, it only took 5-10 seconds. We go in here for items, and we can see that this is actually a visual representation of our database. We can create an item here with strings and representing keys and values, data types, and so on and so forth. And so in about 5-10 minutes, I just showed you how to start up your own Aurora RDS instance with all of the settings, obviously using the defaults, which default to best practices, but also a DynamoDB table, both of which are going to be charged per hour, again, paying per value versus having to get a server and manage getting the most of your database performance out of that. Obviously, remember that in Dynamo, you actually have the benefit of paying for read and write capacity units and then the storage of your data. So if I spin up a table here and don't have any underlying data, or I'm not reading or writing to it, then my bill is going to be very, very small, if nothing at all. In the RDS world, that database does live on an instance, so you have to be mindful of that as well. But small semantic differences, but they come into play as you start scaling up, scaling out, and depending on your particular use case, how you handle things like global replication, read replicas, potentially having caching involved with something like Elasticache. So again, very simple, straightforward showcase of actually getting started with those tools, and you can start digging into the documentation and the getting started guides for starting to put example data in there and building applications that begin to query it. So obviously there's a lot of content and a lot of diving deep that we didn't get to do on today's webinar, but if this content was enjoyable for you, be on the lookout, because we definitely will have more higher or more in-depth content on specifics around some of these databases and grappling with some of those design decisions around data modeling and querying and access. So you may have a more solid grasp on exactly which database will be perfect for your use case.
And if you have any questions or want to go to the GameTech website for more documentation on some of the services that we discussed today,
yeah, follow along with the link here, and that should sort of be your launching pad for a lot of the other GameTech-oriented content, guides, and tutorials that we have here.
All right, folks, thank you for watching.